And I'm going to be solving the Year 11 Electronics mock exam. So the objective of this video is that you'll be able to skip to the questions that you didn't do very well on, and you'll be able to look at those answers while skipping over some of the things that maybe you already understand. Okay. Datasheet here, make sure you use it. Some of my sets forgot that this bit existed here and they got the resistor values wrong later. Diagram shows a control system, the output of light sensing units connected to the interface X, complete by adding analog and digital to each box. Well, the output of this, so analog or digital, analog means that it can be one of very many values, a continuous spectrum of values between two extremes. Digital means that it's one of a set number of values, usually 2. So the output of the light sensing unit here is going to be a continuous thing, so that's going to be analog. The output of this switch, that's either going to be 0 volts or 6 volts, that's digital. And the output of interface X is going to be a digital, because it's going to be some sort of analog to digital converter, isn't it? Here is a sensing unit. Name this component. You can call an LDR. You can write light dependent resistor as well. Vout is 6 volts. What would the voltage across component X be? So if that's 6 volts there, then that has to be the remaining 9 volts across there. So it's going to be 9 volts. What would happen to the voltage Vout if a torch was used to shine light on the circuit? Well, if you think about the resistance with the light level, it does this. So if we increase the light level, we're going to reduce resistance. So R is going to fall. If we reduce the resistance of this, then the voltage across this will drop, meaning that this output here will increase. So that's what we want. So Vout would increase. So it's that one. Give a reason for your answer. So the LDR resistance falls as the light level increases, so Vx falls and Vout rises. Okay. The diagram shows 3 different combinations of resistors. Calculate the effective resistance of each combination. Right, so these 2 resistors are in parallel and they're the same, so we can use the divide by the number of resistors there are rule. So it's just going to be 50 ohms, because we've got 100 ohms and there are 2 of them, so that's 50 ohms. We could also use the equation RT is equal to R1 times by R2 over R1 plus R2, which is this equation you just need to learn. So R1 times by R2 is 100 times by 100 divided by 200, R1 plus R2 is equal to 10,000 divided by 200 is 50 ohms. This one here resistors in series. The total is just the sum of the 2. So that's equal to 2, 0, carry the 1, 620 ohms. And this one here we have to use the formula for, so you can use, I'm going to use the other formula this time just to show you all of the formulae. So we've got 1 over the total resistance is equal to 1 over 120 plus 1 over 240. So the best thing to do at this stage is just to put it in your calculator. 1 divided by 120 plus 1 divided by 240. And we need to flip that back over again. So RT is equal to 80 ohms. That's because 1 divided by answer is 80, so you have to do 1 divided by that to get it. Right, there is actually a shortcut to doing this in this way, which is to say that a 120 ohm resistor is the same as two 240 ohm resistors in parallel. So you kind of got this 240, 240, that's that one, and then you've got another 240 there, like that. So you've got three 240 ohm resistors in parallel, which means that it's equivalent to an 80 ohm. But just use the equations easiest. Okay, very standard question. Lots of people messed up on this. An LED is used to power an indicator, la-di-da. There's a voltage drop of 2 volts across the LED. It even shows you that. So let's write on what we know. That's 6 volts in total, 2 volts across there, so 4 volts is across there. We also know that this current needs to be 15 milliamps. Okay, what's the current flowing through the resistor? 15 milliamps. 1 mark for that, 1 mark for the unit. What's the voltage drop across the resistor? 4 volts. Select the correct equation to calculate the ideal value of the resistor R in kilo ohms. So we need R equals V over I. I think it means select and use here, but never mind. V is, we've got to use the values for the resistor. So we've got to use 4 and 15 times 10 to the minus 3. That's the current there. 4 volts, 15 times 10 to the minus 3. So we shove that in our calculator. 4 divided by 15 times 10 to the minus 3 gives us 266.6 dot 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 ohms. But that's not what it asks for. It asks for it in kilo ohms. So we need to convert that to kilo ohms, which is that 0.267 kilo ohms. State the E24 series one, so there's a little bit more information here. The current flowing through the LED is no more than 15 milliamps, so we have to round our resistor value up to make sure that that happens. So if we look here, we were on 266, so we need to round up to 270. So it's 270 ohms goes there. Question 5. Here are 4 lamps. Select the correct equation to calculate the power used in lamp C. Well, P is equal to I times by V, so it's going to equal 400 times 10 to the minus 3 times by 9. So that is going to be, it's in watts, so it's this one, because that's 0.4 there. What is the power used in lamp C? Well, let's work it out. So it's 0.4 times by 9. Stupidly easy. 3.6 units watts. It's already told you the units up there, so there's no excuse for getting that wrong. Which 2 lamps use the same power? So do we just work them all out then? So this one is 3 by 0.3. So that's 0.9 watts. That one we've already done. This one is 6 times by 0.15, which is 0.9 watts. So it's those two, B and D. There we go. Question 6. Traditional 555 timer. Which other resistor and capacitor will produce a delay of 1.1 seconds? So this is the monostable delay equation, which is governed by this here, T equals 1.1 times by RC. So we need RC to equal 1 second. So which one of these multiply together to make 1? So it's definitely not that one and that one because they've got 2's in them. So let's try this one. 10 times 10 to the 3 times by 100 times 10 to the minus 6 is 1. So it's that pair there. What is the amplitude of the output signal shown in the graph? It's just halfway between there and there, so that's a 10, so it's going to be 10 volts. This is dead easy question. Question 7. Okay, quite a few people came unstuck on this question here, but actually it's really simple. What's the value of I2? So at this junction here, we have 5 milliamps coming in, we have 2 milliamps going that way, so how much flows that way? Well, it's got to be 3 milliamps. So 3 milliamps goes that way. What's the value of V2? Well, we have 9 volts across the whole thing. Between this point and this point is 3 volts, so between this point and this point it's got to be 6 volts. What's the value of V3? Well, we've got 9 volts between here and here, we've got 3 volts between there and there, what's left is 6 volts. Which has to be, they obviously have to be the same because this and this are in parallel, so the potential difference across them are always identical. So it's 6 volts. Here's a temperature sensing unit. Hooray! What is the name of the component labelled X? That's the thermistor, you just need to know it. If Vout were 1 volt, what would be the value of Vx? Well, if that's 1 volt, you've got 5 volts left, so that's got to be 5 volts. What would happen to Vout as component X heated up? Right, so the resistance against temperature is going to look like that. So if we start at some point, then Vout is 1 volt, isn't it, at some value. So let's start here at some temperature, say start temperature. Then Vout is 1 volt. So that's our initial value. What happens as we increase the temperature? Well, as we increase the temperature, this here is going to reduce in resistance. That means that its share of the voltage will reduce, and so Vout will start to increase. But look here, the resistance drops suddenly to start with and then doesn't drop much at all. So the change is going to be big to start with, less later on. So it's not going to be a straight line. So it's going to be something maybe like that. You need it to be increasing in size, and you need it to be non-linear and bending that way. The following circuit is part of a burglar alarm. Input A needs to be a logical 0 when the switch is pressed. So we have a standard pull up resistor, so we need to put the switch in the bottom and a pull up resistor there. So when we push that switch, A is connected to 0. When we release the switch, we still have a 5 volts there. What's the purpose of component named Y? Right, so this one is a pull down resistor, so let's call it that. Okay, its name is a pull down resistor. That would actually be enough to get you the mark, but what's the purpose? It's so that when the switch is not pressed, B is at 0 volts, because if it wasn't there, when the switch wasn't pressed, then B would be floating. It could be any value at all. So the point is when S2 is not pushed, B is at 0 volts. So that's the point. That's what's called a pull down resistor, because it pulls this value down to 0 volts. Question 10, transistor question. This one people found difficult. Okay, but it's a matter of learning your rules on your transistors. The signal from the logic gate here is between 0.5 volts and 7.7 volts. Complete the following table by adding the correct voltages. Okay, if this is 0.5 volts, then the maximum this could be is 0.5 volts. To turn the transistor on, you require 0.7 volts. So the transistor is not conducting. That means no current flowing from here down to here. If no current's flowing here, no current's flowing through this resistor. If no current's flowing through this resistor, V is equal to I times by R. No current means that there's no potential drop across that resistor. No potential drop across that resistor, this side must be the same as that side. So it's got to be 0.5 volts. If this is 7.7 volts, then there is enough to get 0.7 volts across the base to emitter junction of your transistor. And so because this is just like a diode here, in fact that's what that arrow means, it's a diode, so this will be at 0.7 volts and it will start to conduct and it will stop going any higher than 0.7 volts. So it'll be 0.7 volts there. The lamp in this case will definitely be off, the lamp in this case is probably going to be on. The bulb in the lamp is rated at 12 volts 100 milliamps. So let's write that stuff onto the page. Has a current gain HFE of 50. Calculate the base current when it has just saturated. Okay, so when it's just saturated, that voltage there is 12 volts. Okay, so that's what saturated means. It's got no voltage between there and there, so all the voltage must be across there. So that's got to be 12 volts, which if it's just saturated, if that's 12 volts exactly, and it's just gone 12 volts, then that means that the current through the lamp will be at its rated value, which is 100 milliamps. So 100 milliamps is coming down here. If 100 milliamps comes down here, then some amount of current must go like that. And the equation is that IC is equal to IB times by HFE. So IB is equal to IC is 100 milliamps divided by 50. That's equal to 2 milliamps. The logical gate output is 7.7. The transistor is just saturated. What is the voltage drop across the resistor? R. So the voltage drop across here and here is 7.7 on this side, 0.7 on that side, so it's 7 volts. Hence calculate the value of resistor R. So R is equal to V over I. Now you have to use the values corresponding to this. So it's 7 volts divided by the current in the base, which is 2 milliamps. So that's 2 times 10 to the minus 3, which is equal to, that's 3.5 thousand, so 3,500 ohms. Question 11, here's the MOSFET. You need to know each of these connections. So this is the gate, this is the drain, and this is the source. Learn them. Why is a MOSFET often preferred to a NPN transistor to interface with a logical system to a high power motor? Right, so if you have a high power motor over here, then it's going to draw a lot of current, but that still means you still need quite a lot of current to flow into here. Now, logic gates aren't very good at producing large quantities of current, so they're not very good at doing that. So a MOSFET's better because it's got a very high input impedance, which means it draws no current. Logic gates cannot produce writing. Logic gates cannot produce much current. An NPN transistor would require a high base current. A MOSFET needs no gate current because its input impedance is almost infinite. Okay, or just something to this stage that no current enters the gate of the MOSFET, whereas lots of current needs to enter the base of a transistor. In reality, what you would do is you'd use something like a Darlington pair if you wanted to use NPN transistors, which is just two transistors, one after another. They look like this. And then you'd put your motor there. So your current gain would be 50 for the first one, 50 for the second one, so it'd be 2,500, which wouldn't then be an issue for the logic system to output 1/2500th of the required current. Anyway, that's by the by. Let's move on. Oh, these look challenging. Circle the logic gate that has the following truth table. So that is 0001 would be an AND, so that must be a NAND. Circle the logic gate that outputs logical 1 only when both inputs. Right, that's just incredibly easy book learning. Complete the following truth table. X is not A, so that's 1, 1, 0, 0. Q is the NOR of this, so a NOR, well, an OR would be 0, 1, 1, 1, so a NOR is 1, 0, 0, 0. So when they're both 0, you have a 1. Right, so here we go. So it's B and X. So both 0, you have a 1, everything else is a 0. Right, NAND equivalence. This is NAND followed by a NOT, so that's NAND. This one has got to be not A and not B. It's not. A NOR gate. And this one here is that without that, so that's going to be the OR gate there. Some of the NAND gates in the circuit below are redundant. Circle all redundant gates. So we're looking for NOT gates that follow one another. So that's one and that's one. So those two are redundant. And here we've got 1, 2, 3. So two of them are redundant. So you can either have those two or those two. Question 16, we first of all need to select a logic gate to go in this box here. So we need to turn this column into this column, and that's just the opposite. So that's going to be a NOT gate. Next one, we need to turn A and B, these two columns, into Q, which is this column. So it's when they're both high, we get a 1 here and here, so we need an AND gate like so. The effect of the pulse is given on logic page 10. There are no page numbers, I assume it means this. Which two pulses would cause R to go to logical 0? Okay, so this is the NAND of C and A, so it's the NAND of these. So a NAND gate is 0, 0, 0, 1, 1, 0, 1, 1. So an AND gate would be 0, 0, 0, 1. So this is 1, 1, 1, 0. So we want them both to be high in order to get logical 0. So it's that one and that one, 5 and 7. The pulse generator has a period of 2 seconds. What's the frequency? Frequency is equal to 1 over the time period. So it's equal to 1 over 2, which is 0.5 hertz. Right. Continuing on. This truth table shows the initial sequence of outputs from a 4-bit counter. Most significant bit is D. Right, pulses received. How many pulses are needed to produce the following outputs? Well, if it starts at 0, so that's 1, 2. So this, remember, that's the 8s, that's the 4s, that's the 2s, and that's the 1s. So 8 plus 4 plus 1 is 13. So that's the number 13, which corresponds to the 13th pulse, would make that happen. Select the correct output combination after 4 clock pulses. That's going to be, well, after 3 is going to be that, and after 4 is going to be that. So we need that there. The counter resets when the reset input R receives a logical 1. Select the output combination that resets the counter. So it's got to be C and B have got to be high. So it's going to be the first time that C and B are high. So this will reset. That would also reset it, but you'll never get to that one because it will have already reset on this one. Question 18. Relatively easy one. We need the Boolean expression for that. We've only got one thing, so it's got to be not A and not B, which is that one. Part B is the 2 in the middle, so we need A and not B, and we need not A and B, so it's that one there, all together. Okay, question 19. Complete the design for the notification system. If we read the blurb here. Now, a lot of people in my set put in component names in here. You're not going to get the credit for that. So if you put, for instance, here, if you put an op amp, then that's not going to be good enough. So here we need a pulse generator. So I accepted A stable. I didn't accept a 555 timer. Here we have a process which is a logic AND gate. Here we need a driver, or a transducer driver to be better. Transducer driver there, and here we need the high power lamp, which is given to us in the question. All of those boxes are in the first book on the first page. A D-type flip-flop is used as a latch. Complete the circuit diagram. I had lots of people connecting Q back to D. That's only done when you want to turn a latch, when a D-type into a counter. So we need switch A to trigger the latch. So switch A triggers the latch, is easy. We connect that to there. We want it to trigger it, so we want D to be set high. We want switch B to reset the latch. There we go. When you push that, that will go high, which will trigger the reset there. So it's as simple as that for 3 marks. Question 20. Oh, you see, look, they've called it a pulse generator here, which is what you needed to write back there. They've also called it a pulse generator there as well. Here is the block diagram for the traffic lights of a model village. Pulses from the generator come in here. You've got a counter, you've got a reset line, so it resets when C is high, so that'll be on the count of 4. State the Boolean equation for output G. Okay, so that's going to be A NANDed with B. You can also have written that, because that's the same as that if you use De Morgan's theorem between the two. Right, what are the possible states, output states of the counter? So R is just B, so that's going to be 0, 0, 1, 1. Y is just A, so that's got to be, oops, wrong, a 1 there, a 0 there, and a 1 there. G is this node with this one. So that's going to be a 1, that's going to be 1, that's going to be a 1, that's going to be a 0. Now obviously this is a rubbish set of traffic lights, because why you would have the yellow and the green, or the green and the red on at the same time makes no sense, but hey, just roll with it. Okay, a D-type flip-flop can be used as a 1-bit counter. Right, now is when we connect Q back to D. Complete the diagram of the 1-bit counter by adding the connections on the diagram. So pulse generator goes into the clock, and Q goes back to D. So there's my 2 there. The D-type flip-flop is a rising rising edge triggered. On the graph below, label the rising edge. Well, that's a rising edge. Nobody got that wrong, but an awful lot of people didn't do it. The output Q is initially at logic level 1. There it is. Complete its signal. So every time you get a rising edge here, Q will switch to the other state, because this is always the opposite of that, and that's what's fed into D. So here it will go like that, and it will go rising edge there, rising edge there. So it'll go like that, and it will reverse every time you get a rising edge there. Q bar is always the opposite of that. So Q bar will do that. Okay, moving on. The pulse generator is made of the following 555 circuit. This was on the whole done very well by my groups anyway. So we need to use this formula here. F is equal to 1.44 divided by R1 plus 2R2 times by C. So now we need to substitute in the values. So we've got 1.44 divided by R1, which is 1 times 10 to the 3, plus 2 times by R2, which is 22 times 10 to the 3, all times by 10 nanofarads. And this is the bit that if anybody got anything wrong on this, you put -6 there instead of -9. Nanofarads -9. So need to work all that out. So I'm just going to work out the bottom line first, and then I'm going to do 1.4 divided by it. So 1 times 10 to the 3 plus 2 of that is 44 times 10 to the 3. Then I want to times that by 10 times 10 to the -9. So that's the bottom line. Then I do 1.44 divided by that, gives me 3,200. And the units, hertz. Here is a diagram for a counting system. So we've got something, a switch, an AND gate, and Q. The waveform below shows the output produced by the system on an oscilloscope. Okay. The volts per division setting on the oscilloscope is set to that. Determine the amplitude of the signal. Right. The first thing you have to do here, and I imagine most of you just glossed over this, but the first thing you have to do here is realise that this is a digital signal, 0 and 1, which means that the amplitude is the distance between there and there. If this were an analogue signal, then the amplitude would actually be the distance between there and there. Okay, but it's a digital signal, so the amplitude is essentially the height. It's poor language that we use, but it's going to be like that in your GCSE, so bear that in mind. So we just need to count the boxes. So it's 1 full box, 2 full boxes, 3 full boxes. So that's 3 centimeters. So it's 3 times by 7.5 gives you 1522.5 volts. The time base is set to 18 microseconds per centimeter. What a bizarre number. Determine the period of the output signal. So let's start anywhere. 1 box would take us to there. 2 boxes would take us to there. 3 boxes about there. 3 boxes would take us to there. So that's 3 full boxes. So we're halfway between there and there, and we're halfway between there and there. So it's 3 boxes times by 18 is equal to 54 microseconds. Very odd time base to use. Anyway, calculate the frequency. F is equal to 1 over T, which is equal to 1 over 54 times 10 to the -6. So we got 54 times 10 to the -6. 1 divided by it gives us 18,500. So 8,500 hertz, or 18.5 kilohertz. Okay, here we have a capacitor charging circuit. Now, when we close this switch, current's going to flow onto here, charging this capacitor up. But as this capacitor gets more and more charged, then the voltage drop between here and here will be smaller, so less current will flow, meaning that the capacitor will keep charging, but not as quickly. The final value that it's aiming towards is going to be 9 volts. So let's draw that on to start with a little dotted line or something across here. Not an easy grid to see, this one. So just to make sure that we realise that's at 9 volts there. So we're going to start at 0 down here. Now in some set amount of time, you can't, it gives you the axes here, but you can't know, without knowing what the R and C are, how much time has actually, how long it actually takes for this particular circuit. You'd need to know R and C to be able to work that out. But we can do it generally, roughly anyway. So in any set amount of time, it will always get halfway towards its final value. So let's say that's 2 seconds, just for the sake of drawing the diagram. So halfway between here and here is 4.5 volts. That's 5 volts, so that's 4.5 volts there. So we've gone halfway. Halfway between here and here, well, from 4.5 volts to 9 volts, so we want 4.5 plus 9 divided by 2 is halfway between 4.5 and 9 is 6.75. So that's 6, that would be 7, so 6.75 is about there. Halfway again in the next 2 seconds would be maybe about there. Halfway again, half of that is about there. Halfway again in the next 2 seconds, so maybe there. Halfway again would be about there. Halfway again would be about there. So that's the line we need to draw. Okay. Right, now we're asked to increase the capacitance. Well, if you increase either the resistance or the capacitance, the time constant will increase, which means that it will take a longer time. So if you think about this, the capacitor is essentially like a bucket, and you're filling it up with charge. The resistor is essentially the pipe that you're filling it up with. The bigger the resistance, the thinner the pipe. So if you have a bigger bucket or a thinner pipe, then that means it's going to take longer. So it's going to be the exact same shape, but maybe every 4 seconds this time. Let's say we double the capacitance. It's going to be every 4 seconds this time. So every 4, and then 8, well, halfway between there and there. So halfway between there and there is about there. And then at 12 seconds, halfway between there and there, it's going to be about there. It's going to look something like that. Right, now this graph is never flat, it's never horizontal, it never quite reaches 9 volts, definitely don't have it going above 9 volts, has to start at 0, starts off steep, gets shallower and shallower and shallower. The diagram shows a pulse generator connected to the clock input of a decade counter. Okay, so a decade counter, only one of these is high at once. It starts off with this one being high, and then every pulse makes it go on to the next one. So if you wanted this one to be high, it would be after 1, 2, 3 pulses, not the 4th pulse. Add a diagram to the connections of any components needed to reset the counter after inputs 0, 1, 2 and 3 have gone high so that the pattern repeats. So we just need it to be on 4. Because once that goes to 4, that will reset, putting it back to 0, and clock pulse to 1, clock pulse to 2, clock pulse to 3, clock pulse to 4, instant reset back to 0. Okay, the counter operates on a rising edge of the clock pulses, and the initial states is shown in the graph below. I can't really see where it's shown below, so I'm just going to assume that output 0 starts at 1 and all the rest start at 0. If you started here, then everything would just be shifted along a bit. But let's go for it like this. So at the first clock pulse here, output 0 is going to go low, and output 1 is going to go high, like so. They're going to stay the same. At the second clock pulse here, output 1 is going to go low, and output 2 is going to go high, like so. At the third rising edge, output 3 is going to go high, output 2 is going to go low, like so. On the fourth rising edge, this one's going to go low, and it's going to reset back so that output 0 goes high again, and then the pattern repeats. So that one goes up there. No, that's not quite right, is it? So on this rising edge here, that goes down like that. On this rising edge, that one goes there, but nothing changes after that. So that will stay high, this one will stay low, and this one will stay low. Okay, if you started with this as 0, then the whole thing would be offset 2 spaces that way. So you'd start 0, 0, and then that would go high, and everything would be shifted off to the right. That was worthy of the marks as well. The rising edge is required for the counter to function. Students suggest a very simple subsystem to produce a rising edge when a switch is pressed. It's a push switch. So you needed a symbol for a push switch, like so. You needed it to give a rising edge, which means that you need a pull down resistor, which is a 10k resistor, and that's V out there. That's your positive rail. That's your 0 volt rail. And that's all you needed for that one. Question 24. 555 timer is used to produce a simple time delay, so it's set up as a monostable. The time delay is 10 seconds. Select and use an equation to calculate a suitable value of R1. So we're using this equation here. T is equal to 1.1 RC. So T has got to be equal to 10. 1.1 times by R1 times by 100 times 10 to the minus 6. And again, people messed up their units there. So R1 is equal to 10 divided by 1.1 times 100 times 10 to the minus 6. You've got to learn your powers of 10. 10 divided by 1.1 times by 100 exponent minus 6 gives you 91,000. The voltage of the 555 is 8.8 volts. That's 8.8 volts when high. The voltage across each LED is 2 volts. So that there is 2 volts. That there is 2 volts. Okay. We need to R. It's clearly meant to be R2, isn't it? This paper's riddled with errors, isn't it? Orange, black, brown. So orange is 3, black is 0, brown is 1. So it's 3, 0, and then 1 extra 0. So R2 is equal to that many ohms. Calculate the current flowing in each LED. So we need the voltage across this resistor first. Well, if that's 2 volts and that's 8.8 volts, then that must be 6.8 volts. Lots and lots of you took this 2 volts off twice, but look, these two are in parallel. So although they've got 2 volts across each of them, it's the same 2 volts that are across each of them. So this here is just 6.8 volts down from there to there. It's just 8.8, take away 2 volts, because this doesn't matter which way you go. Start here, 8.8 volts, you lose 6.8, you're left with 2, you lose 2, you're left with 0, which is there. Start with 8.8, you lose 6.8, you're on 2, you lose 2, you're on 0. It doesn't matter which way you go, you end up on 0. That 2 volts there and that 2 volts there are the same 2 volts. You can't add them together. So R is equal to V over I. So I is equal to V over R. That's equal to 6.8 divided by 300. 6.8 divided by 300 gives you, press the E and G button to get the milliamps, 22.66 ... milliamps in total. Okay, 22.6 milliamps. Assuming these two LEDs are the same, half of it's going to flow through that, half of it's going to flow through that. So divide that by 2 and we get 11.3 milliamps each. 11.3 milliamps each. Okay. Right, finally, question 25. So this question here was assessing your ability to interpret a flowchart, compare it with the specification, and present your answer using coherent and sensible and logical prose. But you don't actually have to write in prose, you can write in bullet points as well. So it says, evaluate the function against the specification and suggest any improvements that are required to meet the specification. So lots of people answer this in different ways, but those answers that were super clear I gave 6 to. Those answers that hit the 3 mistakes but weren't very clear I gave 5 to. And if you got less than that, then you didn't notice all of the mistakes. Right. So we start here, we set our count to 0. We turn on the red LED, which is what happens here. Switched on for 5 seconds, wait 5 seconds, there we go. Turn it off again. So we've done that, that's happened. Immediately after, these two need to be switched on. So there they are switched on, but it's not immediately after. So I'm going to call that 1 there and that 1 there. After 3 seconds, this light is switched off. No, it's not. The yellow light's switched off instantly. So that is a problem there and there. Then we wait another second, and then we need to turn the green light off, which we are doing there. We need to repeat the sequence 10 times. We start on 0. If we add 2 the first time, 2 the second time, 2 the third time, 2 the fourth time, 2 the fifth time, then we get to C equals 10. So we're going to go yes at that point and stop. So we are only going to go out 5 times, not 10 times. So that's the third mistake there, which you can fix either there or there. Right, so how are we going to present that? Well, there are lots and lots of ways to do that. I'm going to do one way. So I'm going to evaluate it first against the specification, and then at the end I'm going to suggest the improvements to fix it. So on power up, we start. C is initialized to 0. This will count the repeats later. Okay, red light is turned on for 5 seconds as per spec. So we got to here now. Then wait for 2 seconds, which is not in the spec. So I've got to here now. The green and yellow are turned on, but yellow is then turned straight off. No delay of 3 seconds. So that's, we got to here. Then the green light is turned off after 1 second. There's the wait there, it's turning off. So then the green light is turned off after 1 second. It repeats for 5 times, not 10, because it adds +2 to see each repeat. Right, so that's my evaluation. Now I'm going to fix the problems. Fixes. Number 1. Now I've labelled it here, here and here, so it's pretty clear what I'm talking about. Remove, wait 2 seconds. Number 2, add, wait 3 seconds. And number 3, change C equals C plus 2 to C equals C plus 1. Oops, plus 1. Or change is C equal to 10 to is C equal to 20. And that would be enough. Okay, so I've evaluated it here against the specification. I've identified what meets the specification and what doesn't meet the specification. I've then listed all my fixes here. You could have possibly built the fixes into this. I just thought it was easy to separate the two out. And that's the end of the paper.